Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson, and today we are looking at a collection of problems reviewing the problems from a midterm and working on this with one of my students. And this is the sixth question of this particular midterm. So we're given two different points of data. We're told in 2010 that a population of something was 26,000, and in 2015 the population had grown to 41,000. And although the problem doesn't say it, I'm assuming that we have exponential growth. Now, depending on what your book, what your teacher has taught you, there's a couple of ways to approach this. Generally, we either given the differential equation that describes this, or if we're told that it's exponential growth, then we can jump right to the equation that governs exponential growth. So I'll start off with the differential equation. The differential equation says that the rate of the growth of the population with respect to time, which looks like dp dt, is equal to or is proportional to the population, and we represent that by equals k times p. So p is our population, t is our time, and k is a growth constant. And if we work on solving this via a separable differential equation, we divide the p over and multiply the dt over, and so we get something that looks like this: 1 over p dp equals k times dt. So all the terms involving p are to one side, and all the terms involving t, or just not p, are on the other side. And we'll go ahead and integrate both sides here. And on the left-hand side, since that's 1 over p, we get the natural log of the absolute value of p is equal to kt plus our constant of integration. Okay, so now we're trying to solve for p, actually, because t is our independent variable. So we're going to raise both sides as powers on e, and we get that the absolute value of p is equal to e to the kt plus c. So there's a couple of cosmetic changes we do to this to make it look a little bit better, a little bit more palatable. So the absolute value of p is equal to e to the kt, and then we use the law of exponents to turn this sum in the exponent to a product of the bases. And then we take the absolute value and the e to the c, and we put it all into one single constant. You can call it c. There's all kinds of things to call it. Some books will call it p naught because of what it ends up being. And that's probably what we're going to do here. So we're going to call that p naught, and then we have the e to the kt term. So the e to the c and the absolute value becomes p naught. And there's reasons we can do that, largely because all of those things are constant, and we haven't introduced any of our point values yet, and so we don't even really know or care what the signs are of any of these things, or what the values are of p and c. Those can all be embedded into p naught. So now we get our solution to our differential equation. Our population with respect to time is equal to p naught e to the kt. So now what we need to do is figure out what p naught is and what k is. Now, if you look back at our data, we were told that in 2010, the population was 26,000. So we're going to say that 2010 is actually t equals 0. And when t is equal to 0, p is equal to 26,000. And then when in 2015, that's 5 years later, so we're going to say when t is equal to 5, p is equal to 41,000. So let's use that first bit of data to help us find one of our constants. And so when t is equal to 0, we get p of 0, is equal to, that's equal to 26,000. But we also know that that's equal to P naught e to the k times 0. Well, k times 0 is 0. E to the 0 is 1. So that means that P naught is equal to 26,000. Which from the notation, if you've done science, you know that usually the naught notation denotes the initial amount. And so that's our initial amount for our population. I'll rewrite some of this up here. So now we've got P of t is equal to our new P naught, so we know what our initial condition is, times e to the kt. And then we need to figure out what k is. So we know that when t is equal to 5 years after the fact, that this is equal to 41,000. And then that's equal to 26,000 e to the k times 5, because that's t is equal to 5. So now we need to solve this for k. So we'll divide both sides by 26,000. And we get some cancellations here. And we get 41 over 26 is equal to e to the 5k. So we take the natural log of both sides. And we get the natural log of 41 over 26 equals 5k. And so k is equal to 1/5 the natural log of 41 over 26. And you can leave it like that, or you can find a decimal and put that all in. And then we'll have our complete answer. We've got one more bit to do with this problem. So I'm going to write up our full equation here. So P of t is equal to 26,000 e to the k, which is 1/5 times the natural log of 41 over 26 times t. So the part B to this question asks, when will P equal 100,000? So this tells us the population we want, but we need to figure out the time. Well, plug in 100,000 in for P. So 100,000 equals 26,000 e to the 1/5 natural log of 41 over 26 t. And you might get a little bit weary of writing out that huge expression for the exponent, so you can use your calculator to figure out what that value is and put it up as a decimal. So my calculator says 0.091095, and so we're going to make that 0.0911, let's say. Okay, so let's continue solving this for t. So we're going to divide both sides by 26,000. And we're going to lose some zeros here, which will be good. And then we're left with 100 over 26, which we could reduce to 50 over 13. Make it a little bit better. And then that's going to be equal to e raised to the 0.0911 times t. Okay, so now we're going to take the natural log of both sides again. Be able to knock down that exponent. Or you can just jump right to set it equal to the exponent. And so we get the natural log of 50 over 13. I want to go ahead and get a number for that. So 1.347 is equal to 0.0911 t. And then t then will equal 14.79 years. Which should make sense, because in 5 years it went from 26 to 41,000, and that's an increase of about 15,000. So it's not out of the realm of possibility that in 100 and in 14 or 15 years it'll get up to 100,000. So that's it. And those are the answers to both of those questions. Thanks for watching, and I'll see you in the next video.